Okay, let's unpack this. Have you ever been working with different AI tools, maybe different language models or vector databases built with different embedding models and just hit a wall?
Oh, definitely.
You get these outputs, these, complex numerical embeddings representing text from one model,
Yeah.
but they just don't play nicely with a tool or database built for another model's embeddings. They're kind of incompatible.
Absolutely. It's a really common challenge. Each embedding model,
Right.
even if it's trained on similar data for similar tasks, it creates its own unique high-dimensional vector space.
Right.
Think of it like, I don't know, different mapping systems for the same city. One uses GPS coordinates, another uses some local grid reference.
Okay, yeah.
They both describe locations, but the numbers themselves mean different things in each system. So embeddings from one space are, like the sources say, fundamentally incomparable with others.
Right. So you can't just drop embeddings from model A
Yeah.
into a search index built for model B and expect it to work properly.
Nope, not at all.
Bridging that gap is a huge hurdle. And that's exactly what we're digging into today. You brought us this really interesting paper from Jiha and colleagues at Cornell, harnessing the universal geometry of embeddings, plus some notes and a study guide.
Yeah, and our goal here, our mission for this deep dive, is to really explore the core innovation in this work, a method they call vec-to-vec.
Vec-to-vec, okay.
And the breakthrough is that it manages to do something that's been incredibly difficult, translating between these incompatible embedding spaces without needing any paired data.
Unsupervised translation, that sounds like the big deal.
That's the game changer, yeah.
And we'll get into how they pull it off, but also the surprising implications, especially around data security, right?
Yes. We'll use the materials you provided as our map for this.
Yeah.
Let's jump in.
Okay. So first, maybe just quickly recap, what are text embeddings again?
Sure. So they're basically numerical vectors, just lists of numbers that are designed to capture the semantic meaning of text. The core idea is that texts with similar meanings end up as vectors that are close to each other in this, like, high-dimensional space.
Meaning gets turned into geometry, proximity.
Pretty much. Concepts that are related should cluster together. But, like we said, different models, whether it's BERT, T5, Roberta, even multimodal ones like SailClip, which they tested, they create their own unique geometric layout.
So the location for apple relative to banana in one model space is just different from where it is in another model space.
Exactly. And it's not a trivial difference. It means algorithms or databases tuned to the specific geometry of one model space just won't work right with embeddings from another. If you've built, say, a search engine using model A's embeddings and then a better model B comes along,
You can't easily switch your data over because the embeddings don't line up?
you're kind of stuck or facing a massive retraining effort.
Okay, so that's the problem. It seems pretty fundamental. What's the big idea, the theoretical leap that Jeha and colleagues are proposing to tackle this?
Well, their work is really anchored in this fascinating theoretical concept they call the strong Platonic Representation Hypothesis.
Okay.
It builds on this existing, maybe slightly vaguer idea that large AI models might converge on some kind of shared internal understanding, especially seen in image models.
Right, the original Platonic Representation Hypothesis. So what makes this one strong?
The strong part is that they're making a more constructive claim, specifically for text models. They don't just hypothesize that a universal latent structure for text meaning exists. They propose that this structure can actually be learned, and crucially, that you can use it as a bridge to translate between different models' representations without needing any paired data.
Ah, okay. So it's not just it might exist, it's we think we can find it and use it for translation.
Precisely. It's a constructive hypothesis. It's the theoretical bedrock that makes their method, vec-to-vec, even conceivable. The core belief is that different models, if they're trained with similar goals on similar kinds of data, like text,
Yeah.
they'll end up learning representations that, despite surface differences, share this deeper universal geometric structure.
Okay, so the theory suggests is possible. How did they actually build vec-to-vec to do this unsupervised translation? This feels like the key methodical innovation.
It really is. Vec-to-vec is presented as the first method that can do unsupervised embedding translation between arbitrary text models. Before this, if you wanted to map embeddings from model A to model B, you usually needed what's called paired data.
Meaning you needed the embedding of the exact same text from both models.
Exactly. You'd feed the same sentence to model A and model B, get both embeddings, and that pair acts as a direct translation example. Vec-to-vec gets rid of that requirement completely.
So what's the specific problem vec2vec is designed for? Let's say you get a hold of some embeddings, maybe from a database dump, but you don't have the original text.
Right, or you don't know what model even created them.
Yeah. So the problem is, take this set of unknown embeddings from an unknown source model, let's call it M1, and translate them into the space of a model you do know, M2.
And you have to do this without the original text, without knowing what the correct M2 embeddings should be, and without needing deep details about either M1 or M2. Success hinges entirely on learning that hypothesized common geometric structure.
That sounds incredibly ambitious. How does the architecture make that possible?
It's a pretty clever modular design. They took inspiration from unsupervised image-to-image translation networks like CycleGAN, but adapted it for embeddings. Instead of convolutional neural networks, CNNs, which are great for images.
Because they look for spatial patterns.
Exactly. Embeddings are just lists of numbers. They don't have that kind of inherent 2D or 3D spatial structure, so they use multi-layer perceptrons, MLPs, instead. The key pieces are, first, input adapters. Think of these as entry gates. They take embeddings from a specific model space, like M1s, and map them into this proposed universal latent space.
Into the common ground.
Right. Then there's a shared backbone network. This is where the main processing happens, operating within that universal latent space. The idea is this network learns to work with the core universal meaning.
Okay, adapters in, backbone processes.
And finally, output adapters. These map the representation from the shared latent space back out into a specific model space, either back to M1 space for training checks or into M2's space for the actual translation.
So translation from M1 to M2 is go through M1's input adapter, through the shared backbone, then out through M2's output adapter.
That's exactly the path. Output adapter M2 composed with backbone, composed with input adapter M1. They also define reconstruction paths going from a space, through the backbone, and back to the same space, which are vital for training.
I saw some of the figures in the paper, like figure 1 and 4. They show visually how embeddings that start really far apart in their original spaces end up incredibly close, almost overlapping, once they're mapped into vec2vec's latent space.
Yes. Those visualizations are really powerful evidence supporting the hypothesis and showing the architecture is doing what it's supposed to, finding that common geometric structure.
But just mapping to a common space isn't the whole story, right?
Yeah.
You need to make sure the meaning isn't lost or distorted in translation.
Absolutely crucial point. This is where standard adversarial training, like in JANs, often falls short. A JAN might learn to make translated embeddings that look statistically like they belong in the target space, but they could be semantically meaningless or scrambled.
So they needed extra guardrails during the optimization, during the training.
Exactly. This is another major area of academic innovation in the paper. They use adversarial losses, sure, to help the generated embeddings match the distribution of real ones in the target space and the latent space. But they added these crucial generator constraints specifically to preserve semantic meaning without paired data.
Okay, what are these constraints?
There are three key ones. First, reconstruction loss. This is like self-consistency. If you take an embedding, translate it to the latent space, and then immediately translate it back to its original space using the network.
It should end up pretty close to where it started.
Exactly. It forces the latent representation to be faithful, to hold enough information to reconstruct the original accurately.
Makes sense. What's the second?
Cycle consistency loss. This is really clever. It acts as their unsupervised stand-in for knowing the correct translation. Imagine translating from English to French, and then taking that French result and translating it back to English using the network's other path.
Okay.
The cycle consistency loss demands that the final English output be very close to the original English input you started with. It enforces a round-trip consistency.
So you check A to B to A without ever needing to know the perfect B.
Precisely. It's an elegant solution for unsupervised training.
And the third constraint?
Vector space preservation loss, or VSP loss. This one focuses on maintaining the relationships between embeddings. If, in the source space, dog is close to cat but far from car, the VSP loss encourages the network to ensure that after translation, the translated dog is still close to the translated cat but far from the translated car in the target space.
So it preserves the neighborhood structure, the semantic map?
Exactly. It's vital because downstream tasks like similarity search totally depend on these relative distances.
Okay, so it's this combination. Adversarial loss for realism, plus reconstruction, cycle consistency, and VSP for semantic faithfulness. And the paper showed you really need all of them.
Absolutely. Their ablation studies, where they removed each component one by one, showed that translation quality dropped significantly without any single piece. They all work together. It's a very well thought out optimization strategy.
Right, a synergistic effect. Okay, theory sounds good. The method seems intricate and clever. Did it actually work? What did the experiment show?
They really put it through its paces. They used diverse datasets trained mainly on natural questions, NQ, from Wikipedia, but tested on NQ plus things like tweet topic.
Tweets. That's very different from Wikipedia.
Very different. Colloquial language, emojis, the works, and also MIMAC, a dataset of hospital intensive care unit notes, highly specialized medical jargon.
Wow, okay. That's a tough test for universality.
That was the point, to see if it learned something truly universal or just, Wikipedia-specific geometry. They also tested translations between models with totally different architectures, T5, BERT, Roberta, even CLIP.
CLIP, the one trained on images and text.
That's the one. So really pushing the boundaries.
And the results. How good was the translation quality? Metrics like cosine similarity, accuracy.
For in-distribution data, like translating between models both evaluated on NQ, vec2vec did exceptionally well. Cosine similarity is up to 0.92, which is very high, and even a 100% top one accuracy in finding the correct match in some cases. Near optimal performance.
Impressive for the home turf.
Yeah.
But the real test is cross-backbone and out-of-distribution, right?
Exactly. And this is where the strong Platonic Representation Hypothesis gets really strong backing. When translating between different model families, like a granite model and a GTR model, vec2vec was, and I quote, far superior on all metrics compared to a baseline that doesn't translate the geometry.
And a baseline was like random guessing.
Pretty much, yeah. It showed just how incompatible the original spaces are. vec2vec clearly learned to bridge that gap effectively.
Okay, and the really tough stuff, tweets and medical notes.
Ooh. This is maybe the most striking result. Even though it was only trained on Wikipedia text, vec2vec worked remarkably well, translating embeddings related to casual tweets and complex medical terms like alveolar periostitis.
Seriously, it preserved the meaning of specialized medical terms.
Apparently so, well enough for downstream tasks. The fact that it handled such domain-specific and out-of-distribution language strongly supports the idea that it tapped into a geometry that's more universal than just its training data.
And you mentioned CLIP. It could translate to from an image text model space.
Yeah, they showed results for that too. It wasn't quite as perfect as text-to-text, but it still significantly beat the baselines. It hints that this approach might even work down the line for bridging representations across different modalities.
Like text and images, maybe? Without needing one giant model trained on everything.
Potentially, yeah. It's an exciting hint of broader applicability.
And it didn't need a ton of data from the unknown source model either.
That's right. They found that using just 50,000 embeddings from the source model gave results that were almost as good as using 1 million. So it's relatively data efficient to get started.
Okay, so we have the theory, strong Platonic representation. We have the method, vec2vec, with its clever, unsupervised constraints. And we have the proof it works across models, across diverse data. What's the big consequence? What does this enable that we couldn't do before?
Right. This is where it gets really significant and, frankly, a bit worrying from a security perspective. Having successful unsupervised translation means you can take existing tools built for known embedding spaces.
Like information extraction tools, classifiers.
Exactly. And you can now apply them to embedding data from unknown sources, sources you previously couldn't analyze because you didn't have the right model or the paired data.
Like that hypothetical vector database dump from a proprietary model.
Precisely. They demonstrated this with 2 key tasks: zero-shot attribute inference and embedding inversion.
Okay, what's attribute inference in this context?
They translate the unknown embeddings into a known space, say the space of a standard BERT model. Then they'd use existing methods in that known BERT space to infer attributes like predicting the topic of a tweet, or the medical diagnosis from a memic note embedding just by seeing which known attribute embeddings were closest.
And how well did that work using the translated embeddings?
Remarkably well. On tweet topic and memaic, doing inference on the vec2vec translated embeddings consistently outperformed the naive baseline that's trying to do inference without any translation.
Okay, better than doing nothing.
But here's the kicker. In some cases, inference on the translated embeddings even performed slightly better than what they called the ideal zero-shot baseline.
Wait, better than ideal? How?
The ideal baseline assumes you magically had the perfect original embeddings in the target space. The fact that inference on Vec2's Vex translations sometimes beat that suggests the translation process might even be denoising or aligning the semantics in a beneficial way for that specific task. It's strong evidence of just how well the semantic structure is preserved, maybe even enhanced.
Wow. Okay, so it maintains meaning incredibly well for inference. What about the other task, embedding inversion, trying to get the original text back?
Yeah, this is where the alarm bells really start ringing. They took standard, off-the-shelf inversion models designed to guess the text that might have produced a given embedding and just fed them the embeddings that had been translated by Vec2Vec.
So translate first, then try to invert. And could they actually recover the original text?
Not always perfectly, not verbatim reconstruction every time, but the results were alarming. For some model pairs, they found they could extract meaningful information from as many as 80% of documents just by translating the embeddings and then running inversion.
80%. That's huge. Even partial reconstruction could be bad.
Exactly. Even partial reconstructions often revealed highly sensitive information.
Like what? What kind of information did they actually get back?
From datasets like the Enron emails or MIME medical records, they recovered things like individual and company names, dates, promotions, financial information, outages, and even lunch orders. Specific stuff.
Lunch orders. Okay, maybe less sensitive, but still.
Right, but from the medical data, they extracted specific diagnoses, clinical details. Figure 6 in the paper has concrete examples. You can see fragments of emails, snippets of medical notes, all reconstructed just from the translated embeddings.
This is a major finding. It fundamentally changes the threat model for vector databases.
It does.
An attacker gets only the embeddings, no original text, no knowledge of the source model. They can use Vec2Vec to translate them into a space they do know, and then use existing tools to pull out sensitive data.
That's the implication. The paper states it pretty clearly. An adversary with access only to embedding vectors can extract sensitive information about the underlying documents, sufficient for classification and attribute inference. It exposes a really significant vulnerability. Embeddings, which we often think of as abstract or anonymized.
They're not as safe as we thought. They reveal almost as much as their inputs.
Pretty much sums it up.
That really forces a rethink about security for any system relying on embeddings. Where does Vec2Vec fit in the bigger research landscape? How does it relate to other work?
It carves out a distinct niche. It's different from representation alignment, which usually just measures similarity and often needs paired data rather than translating. It goes beyond simpler unsupervised transport methods because it actively generates new embeddings in the target space. And crucially, it enables embedding inversion on embeddings from unknown models, which wasn't really feasible before.
It also seems complementary to things like multimodal models, maybe offering a way to connect different specialized models after the fact.
That's a good way to put it. The authors themselves see these results as just a lower bound. They think future algorithmic improvements, maybe more stable training, could lead to even better translations, scaling to more data, more models, maybe even more modalities.
So future work might involve refining the training, maybe building inverters specifically designed for translated embeddings.
Exactly. Things like addressing Jan instability, making the training more robust, and developing specialized tools for the downstream tasks.
Okay, so wrapping this deep dive up, we've seen really compelling evidence for this strong Platonic representation hypothesis, this idea that a universal semantic geometry exists in text embeddings, and crucially that it's accessible.
Yeah, foundational theoretical insight.
Then we looked at Vec2Vec, the first method to really leverage this for unsupervised translation between models. No paired data needed, thanks to that clever architecture and those essential constraints. Reconstruction, cycle consistency, VSP loss.
And the experiments really back it up, showing it works across different models, even on really out-of-distribution data, supporting that universality claim.
But the biggest takeaway, the one with immediate practical implications, is the security angle. The ability to extract sensitive information from translated embeddings blows open a vulnerability in vector databases.
It definitely changes the calculus for securing embedded data.
Absolutely. It leaves you thinking. If different models trained on similar tasks are converging on this shared understanding, as Vec2Vec suggests, what does that really tell us about how AI learns representations? And maybe more urgently, how much of the data we think is safely encoded in these systems is actually decipherable if someone has the right tools, like this?
A really important question, both for the future of AI development and for security practitioners today.
Definitely food for thought. Thanks for walking us through the source material on this one.